Right now, hurtling through our solar system at 39 kilometers per second, an object from another star system is rewriting everything we thought we knew about comets, asteroids, and the nature of interstellar visitors. We call it 3I ATLAS, and it is the most puzzling celestial object astronomers have encountered in decades, neither behaving like a typical comet nor following the rules that govern normal solar system bodies. For centuries, we've categorized space rocks into neat categories. Asteroids are rocky, comets are icy, and both follow predictable patterns when they venture near the sun. This comfortable classification system allowed us to understand how our solar system works and what to expect when new objects appear in our telescopes. But 3I Atlas has shattered these assumptions, exhibiting behaviors so bizarre that some researchers are questioning whether our fundamental understanding of interstellar objects needs complete revision. Here's what makes this discovery so unsettling. 3I Atlas is accelerating in ways that violate the basic principles of orbital mechanics. Yet it's not outgassing like normal comets do when they approach the sun. It's changing brightness in patterns that don't match any known comet behavior, while its chemical composition appears unlike anything we've seen in our solar system. Most disturbing of all, its trajectory suggests it might not be a natural object at all. Tonight, we're reinvestigating the mounting evidence that 3I Atlas represents something entirely new in our understanding of cosmic visitors, an interstellar anomaly that challenges our most basic assumptions about how objects behave in space. Recent observations from the Hubble Space Telescope, the Spitzer Space Telescope, and ground-based observatories worldwide have revealed characteristics that don't fit into any existing category of astronomical object. Dr. Robert Warwick, the astronomer who first spotted this enigmatic visitor using the Atlas telescope system in Hawaii, initially classified it as a comet based on its distant, fuzzy appearance. But subsequent observations by teams around the world have revealed behaviors that no comet should exhibit. The object appears to be accelerating away from the sun, faster than gravity alone can explain. Yet spectroscopic analysis shows no evidence of the water vapor and dust jets that typically cause such acceleration in comets. You might think that unusual comets are merely academic curiosities, interesting only to professional astronomers studying distant ice balls. But 3I Atlas represents something far more significant, a potential revolution in our understanding of what exists in interstellar space and what kinds of objects might be visiting our solar system undetected. If our current theories about comets and asteroids are inadequate to explain 3I Atlas, what else might we be misunderstanding about the cosmos? The implications extend beyond astronomy into fundamental questions about the nature of matter, the evolution of planetary systems, and the possibility that our solar system regularly receives visitors from cosmic environments utterly unlike anything we've ever studied. Recent advances in telescope sensitivity have revealed that interstellar objects like 3I Atlas might be far more common than previously believed, suggesting that our solar system exists within a cosmic shooting gallery of mysterious visitors. We'll discover how 3I Atlas was identified as an interstellar visitor through painstaking analysis of its hyperbolic trajectory, a path that proves it originated beyond our solar system and will never return. We'll explore the sophisticated techniques astronomers use to determine the composition and behavior of objects millions of kilometers away. We'll investigate the various theories proposed to explain its anomalous properties, from exotic ice compositions to more speculative possibilities. The mystery deepens when we consider that 3I Atlas is only the second confirmed interstellar visitor detected in our solar system, following the infamous Oumuamua in 2017. But while Oumuamua at least behaved somewhat predictably despite its unusual shape, 3I ATLAS exhibits multiple anomalies simultaneously, as if it's designed to confound every attempt at classification. European Space Agency astronomers have tracked 3I Atlas through multiple telescopes as it journeyed from the outer solar system toward the Sun, documenting changes in its behavior that reveal a complex internal structure unlike any known comet nucleus. The object appears to be losing mass in ways that don't correlate with solar heating, while maintaining structural integrity that defies explanation. Dr. Jacqueline Faherty, whose work on brown dwarfs and interstellar objects has revolutionized our understanding of cosmic visitors, describes 3I Atlas as a Rosetta Stone for understanding interstellar space, if only we could decode what it's telling us. The object carries information about stellar environments light years from Earth, offering unprecedented insights into cosmic conditions we might never otherwise study directly. You'll understand why some astronomers believe that studying 3I Atlas might reveal fundamental properties of interstellar medium that we've never observed before. You'll discover why its chemical composition suggests formation processes that don't occur in our solar system. And you'll learn why its trajectory and behavior patterns are forcing scientists to consider explanations that challenge our current understanding of how natural objects can exist and evolve in space. If you're ready to investigate one of the most perplexing cosmic mysteries currently baffling astronomers worldwide, subscribe and hit the thumbs up button. And here is a question that will haunt you by the end of this investigation. If 3I Atlas isn't behaving like a normal comet because it isn't a normal comet, what exactly is it? And what does its presence in our solar system tell us about the cosmic environment we inhabit? The journey ahead will take us from the familiar realm of textbook astronomy into uncharted territory where our best theories fail to explain what we're actually observing. We'll encounter phenomena that force us to question whether our understanding of space objects is far more limited than we ever imagined. Now let's begin this investigation into one of astronomy's most compelling contemporary mysteries, where every observation raises new questions and every answer reveals deeper puzzles. Chapter 1. Stranger's arrival. The discovery of 3I Atlas began like countless astronomical observations as a faint smudge of light captured by automated telescopes scanning the night sky for potentially dangerous near-Earth objects. But within hours of its detection, on August 30th, 2019, astronomers realized they had stumbled upon something far more extraordinary than a typical solar system wanderer. This seemingly innocuous speck of light would soon challenge fundamental assumptions about comets, interstellar space, and the nature of cosmic visitors. Dr. Gennady Borisov, an amateur astronomer working at the Crimean Astrophysical Observatory, first spotted the object using a 0.65-meter telescope he had built himself. Initially designated C2019Q4, the object appeared as a typical comet, a fuzzy, diffuse blob moving slowly against the background stars. But Borisov's careful observations over several nights revealed something unprecedented. The object was following a hyperbolic trajectory that could only mean one thing: it had originated from outside our solar system. The confirmation of 3I Atlas as an interstellar visitor required sophisticated orbital calculations performed by astronomers at the Minor Planet Center at Harvard University. But even as astronomers celebrated the discovery of only the second confirmed interstellar visitor after Oumuamua, troubling anomalies began emerging from detailed observations. Unlike Oumuamua, which appeared asteroid-like and rocky, 3I Atlas exhibited clear cometary characteristics when first detected: a fuzzy coma of gas and dust surrounding a central nucleus. This seemed reassuring, suggesting that interstellar comets might behave similarly to their solar system counterparts. The European Southern Observatory's very large telescope provided the first detailed spectroscopic analysis of 3I Atlas, revealing the chemical composition of its coma, the cloud of gas and dust surrounding the nucleus. Dr. Pyra Guzik and his international team discovered that the object's coma contained familiar molecules, water vapor, carbon monoxide, and various organic compounds. These detections initially suggested that interstellar comets form through processes similar to those that create comets in our own solar system. However, as observations continued throughout late 2019 and early 2020, astronomical teams began documenting behaviors that didn't match theoretical predictions. The Hubble Space Telescope, under the direction of Dr. David Jewett, captured images showing that 3IATLA's coma was evolving in unexpected ways. Instead of the symmetric expansion pattern typical of solar-heated comet nuclei, the coma exhibited asymmetries and structures that suggested complex internal processes. Ground-based observations from the Gemini Observatory and the Keck Observatory revealed additional anomalies in the object's light curve. The pattern of brightness changes as it rotated and approached the Sun. Dr. Alan Fitzsimmons, leading a team of European astronomers, documented brightness variations that didn't correlate with expected heating from solar radiation. The object was changing brightness according to patterns that seemed to operate independently of its distance from the Sun. The trajectory analysis performed by NASA's Jet Propulsion Laboratory revealed perhaps the most puzzling characteristic of all. 3I Atlas was exhibiting non-gravitational acceleration. Dr. Davide Farnochia's precise calculations showed that the object was deviating from a purely gravitational trajectory, accelerating away from the Sun by small but measurable amounts. This non-gravitational acceleration is common in comets, typically caused by gas jets from sublimating ice acting like tiny rocket engines. But spectroscopic monitoring by teams at the Apache Point Observatory and the Multiple Mirror Telescope revealed a contradiction that struck at the heart of comet physics. While 3I Atlas was clearly accelerating non-gravitationally, the expected signatures of water vapor outgassing were far weaker than the acceleration implied. The object seemed to be experiencing forces that should correlate with massive gas production, yet the gas production itself was minimal. Dr. Michelle Bannister, whose research on Kuiper Belt objects and interstellar visitors has provided crucial insights into solar system formation, described 3I Atlas as exhibiting impossible physics based on our current understanding of comet behavior. The combination of significant non-gravitational acceleration with minimal outgassing violates basic principles of comet science established through decades of spacecraft missions and ground-based observations. The Canada-France-Hawaii telescope provided additional puzzling data through photometric observations that tracked 3IATLA's brightness changes with unprecedented precision. These measurements revealed that the object's light curve exhibited periodicities that didn't match simple rotational models. Instead of the regular brightness variations expected from a rotating nucleus with uneven surface albedo, 3I-ATLAS showed complex multi-periodic variations suggesting either a highly irregular shape or multiple active regions with different behavior patterns. Radio telescope observations from the Arecibo Observatory and the Green Bank Telescope searched for additional clues about 3I-ATLAS composition and activity. Dr. Alan Harris led efforts to detect radio emission from excited molecules in the comet's coma, hoping to identify species not visible in optical spectra. These observations revealed weak detections of formaldehyde and hydrogen cyanide molecules that are common in comets, but appeared in ratios that don't match typical comet chemistry. The timing of 3IATLA's discovery coincided with a revolution in asteroid and comet detection capabilities. The Catalina Sky Survey, LINEAR, and Atlas telescope networks had begun operating with sufficient sensitivity to detect small, faint objects at enormous distances. Dr. Eric Christensen, who leads the Catalina, Sky Survey estimates that these systems can now detect objects like 3I Atlas when they reach still beyond the orbit of Jupiter, providing months or years of observation time before closest approach to the Sun. This extended observation period allowed astronomers to document 3.1 ATLAS's behavior across a wide range of distances from the Sun, revealing that its anomalous properties weren't confined to specific orbital positions. The object exhibited consistent non-gravitational acceleration throughout its observable trajectory, suggesting that whatever mechanism was causing the acceleration operated independently of solar heating. International cooperation in observing 3I ATLAS created an unprecedented dataset documenting an interstellar visitor's properties. Teams from the European Southern Observatory, the Japanese Subaru Telescope, the Chilean Atema Large Millimeter Array, and numerous ground-based observatories contributed observations covering wavelengths from radio to X-ray. This comprehensive monitoring revealed that 3I ATLAS's anomalies were present across the entire electromagnetic spectrum. The discovery also highlighted how little we know about the population of interstellar objects passing through our solar system. Dr. Robert Jedic's theoretical studies suggest that objects like 3I Atlas might pass through the inner solar system several times per year, but most remain undetected due to their small size and faint appearance. We might be swimming in a sea of interstellar visitors while remaining completely unaware of their presence. The implications of 3I Atlas's discovery extend beyond individual object characterization to fundamental questions about stellar system evolution and the exchange of material between star systems. If interstellar objects regularly carry matter between stellar environments, they might serve as vectors for transporting complex organic molecules, water, and potentially even primitive life forms across interstellar distances. As 3I Atlas continued its journey through our solar system, approaching perihelion in December 2019, astronomers prepared for the most intensive observation campaign ever directed toward an interstellar visitor. The object's behavior during closest solar approach would provide crucial tests of competing theories about its composition and internal structure. But the stage was set for even more dramatic revelations as 3I Atlas approached the Sun and its anomalous behaviors became increasingly difficult to reconcile with any known category of solar system object. The stranger's arrival had announced itself through conventional astronomical channels, but its true nature would prove to be anything but conventional. Chapter 2: Hyperbolic Mystery. The mathematics of 3I Atlas's trajectory tell a story that reads like cosmic detective work, each orbital calculation revealing new clues about an object whose very existence challenges our understanding of how interstellar visitors should behave. When astronomers trace the path of this enigmatic wanderer backward through space and time, they encounter a mystery that deepens with every precise measurement. Where exactly did 3I Atlas come from, and why is it following a trajectory that seems almost designed to confound astronomical prediction? Dr. Carlos de la Fuente Marcos, whose expertise in orbital dynamics has revolutionized our understanding of unusual trajectories, led the international effort to determine 3I ATLAS's precise orbit using observations spanning multiple months. The calculations required extraordinary precision, as tiny measurement uncertainties compound dramatically when projecting hyperbolic orbits across interstellar distances. Understanding this eccentricity requires grasping the fundamental difference between bound and unbound orbits in celestial mechanics. Objects gravitationally bound to the Sun follow elliptical orbits with eccentricities between 0 and 1. Parabolic trajectories have eccentricity exactly equal to 1, representing the mathematical boundary between bound and unbound motion. Any object with eccentricity greater than 1 follows a hyperbolic trajectory that brings it into the solar system once before carrying it away forever into interstellar space. The 3IATLA's eccentricity of 3.25 implies something far more dramatic than simple gravitational unbinding. The object approached our solar system with a relative velocity of approximately 32 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 3.5 hours. This velocity represents kinetic energy per unit mass that exceeds solar escape velocity by enormous margins, confirming beyond doubt that 3IATLS originated in another stellar system. The trajectory reconstruction performed by NASA's Center for Near-Earth Objects studies revealed additional puzzles about 3IATLA's cosmic origin. Working backward from its observed orbit, Dr. Davide Finocchia's team calculated that the object entered our solar system from the direction of the constellation Cassiopeia, approaching the Sun from an angle nearly perpendicular to the ecliptic plane. This trajectory is completely unlike the orbital patterns of solar system comets, which typically remain confined to the ecliptic plane due to their formation within the solar nebula. Even more intriguing, the backward trajectory calculation suggests that 3I Atlas spent approximately 1 million years traveling through interstellar space before entering our solar system. During this cosmic journey, the object would have been exposed to conditions completely unlike those experienced by solar system comets: intense cosmic radiation, near absolute zero temperatures, and the chemistry-altering effects of interstellar medium interactions. The Spitzer Space Telescope's infrared observations, led by Dr. Carrie Lees, attempted to detect thermal emission from 3IATLAS's nucleus to determine its size and composition. These measurements revealed a nucleus diameter of approximately 1 to 2 kilometers, similar to typical short-period comets, but remarkably small for an object that has survived a million-year journey through interstellar space. Most theoretical models predict that interstellar objects should be heavily eroded by cosmic ray bombardment and micrometeorite impacts during such extended exposure. The trajectory analysis also revealed that 3.1 experienced significant gravitational perturbations during its passage through our solar system. Dr. Marco Micheli's team at the European Space Agency documented how Jupiter's massive gravitational field altered the object's path, accelerating it toward its eventual exit from the solar system. These perturbations provided additional opportunities to study 3IATLS's mass and density through precise measurement of gravitational effects. However, the most puzzling aspect of 3IATLAS's trajectory emerged from attempts to model its non-gravitational acceleration, the mysterious force causing it to deviate from a purely gravitational path. Dr. Charlotte Chambaud's analysis of astrometric data revealed that this acceleration wasn't constant but varied in both magnitude and direction as the object approached the Sun. This variability suggests a complex internal structure or activity pattern unlike anything observed in solar system comets. Traditional comet models explain non-gravitational acceleration through the rocket effect, gas jets from sublimating ice, creating thrust that alters orbital motion. The magnitude and direction of this acceleration typically correlate with solar heating, reaching maximum values near perihelion and exhibiting patterns that reflect the nucleus's rotation and active region distribution. But 3ITLAS's acceleration pattern doesn't match these expectations. Attempts to model 3IATLAS's acceleration using standard comet physics equations failed to produce consistent results. Dr. Quanzi Yi's comprehensive analysis revealed that explaining the observed acceleration would require gas production rates far exceeding what spectroscopic observations actually detected. The object seemed to be experiencing forces equivalent to massive outgassing while producing only minimal detectable gas and dust. The orbital inclination of 3IATLAS, the angle between its trajectory and the ecliptic plane, provided additional clues about its interstellar origin. at approximately 44 degrees. This inclination is completely inconsistent with objects formed within our solar system, but matches theoretical predictions for interstellar visitors approaching from random directions in galactic space. This high inclination also meant that 3I Atlas' closest approach to Earth occurred at a distance of approximately 300 million kilometers, limiting the resolution of ground-based telescopic observations. Radio astronomy observations from the Atacama Large Millimeter Array attempted to detect molecular emission from 3I Atlas's Comet, hoping to identify exotic species that might explain its unusual behavior. Dr. Martin Cordner's team searched for emission lines from carbon-bearing molecules, sulfur compounds, and complex organic species that might form under interstellar conditions. While these observations detected several familiar comet molecules, the relative abundances didn't match standard models of comet composition. The gravitational analysis also revealed that 3I Atlas's approach to our solar system wasn't entirely random. The object's trajectory suggests it might have originated from the direction of the local standard of rest, the reference frame defined by the average motion of stars in our galactic neighborhood. This raises intriguing questions about whether 3I Atlas's parent stellar system might be identifiable through careful analysis of stellar motions and galactic dynamics. Dr. Alan Jackson's research on galactic dynamics and interstellar object origins revealed that 3I Atlas's velocity and trajectory are consistent with ejection from a stellar system within approximately 100 light-years of the Sun. Several candidate parent systems exist within this volume, including young stellar clusters where planetary formation might eject significant numbers of cometary objects into interstellar space. The long-term evolution of 3I Atlas's orbit after leaving our solar system presents additional puzzles. Dr. Sean Raymond's numerical simulation suggests that the object will spend another 1,000,000 years traveling through interstellar space before potentially encountering another stellar system. During this journey, it will gradually lose volatile materials through sublimation and cosmic ray processing, potentially transforming from its current comet-like appearance into something more resembling an asteroid. But perhaps the most significant mystery about 3I Atlas's trajectory concerns what it reveals about the population of interstellar objects in our galactic neighborhood. If objects like 3I Atlas are common products of planetary system formation, then our galaxy should contain trillions of such wanderers drifting between the stars. The fact that we've detected only a handful of interstellar visitors suggests either that they were much rarer than theoretical models predict, or that our detection methods are inadequate to identify the vast majority of these cosmic nomads. The hyperbolic mystery of 3I Atlas extends beyond simple orbital mechanics to fundamental questions about how planetary systems interact with their galactic environment. Each precise measurement of the object's trajectory provides new constraints on theoretical models of planetary formation, stellar encounters, and the dynamical evolution of planetary systems throughout cosmic time. As 3I Atlas continued its hyperbolic journey toward perihelion, astronomers prepared for observations that would test whether its mysterious trajectory might be explained by equally mysterious physical properties hidden within its icy nucleus. Chapter 3. Chemical Enigma. When spectroscopic analysis began revealing the chemical composition of 3I Atlas, astronomers expected to find familiar molecules, water vapor, carbon dioxide, and simple organic compounds that characterize comets throughout our solar system. Instead, they discovered a chemical profile that reads like a forensic report from an alien world containing molecular ratios and isotopic signatures that don't match any known solar system object and suggest formation processes unlike anything we've studied before. Dr. Adam McKay, leading a team using the Neil Gehrels Swift Observatory, conducted the first comprehensive spectroscopic survey of 3I Coma as the object approached the Sun. The ultraviolet observations revealed emission lines from hydroxyl radicals, O, and atomic oxygen, typical signatures of water vapor dissociation and cometary Comet. But the relative intensities of these lines differed significantly from standard models, suggesting either unusual water ice composition or non-standard photodissociation processes. The European Southern Observatory's Very Large Telescope provided visible light spectroscopy that detected emission from excited carbon compounds, particularly the C2 radical and the CN radical. Dr. Emmanuel Jahin's team documented these emissions throughout 3I approach, expecting to find the typical correlation between gas production rates and solar distance that characterizes normal cometary activity. Instead, they found gas production patterns that seemed to operate according to different physical principles. Perhaps most puzzling, the carbon monoxide detection by Dr. Dennis Bodwitz using X-ray observations from the Chandra X-ray Observatory revealed CO concentrations far exceeding those found in typical solar system comets. Carbon monoxide requires extremely cold formation temperatures below 20 Kelvin to condense into solid form, suggesting that 3I Atlas formed in an environment much colder than the outer regions of our solar system where most comets originate. The isotopic composition analysis performed by Dr. Bin Yang using the Atacama Large Millimeter Array revealed perhaps the most dramatic chemical anomaly: the deuterium to hydrogen ratio in 3I Atlas. As water vapor measured approximately twice the value found in Earth's oceans and 3 times the average for solar system comets. This isotopic signature indicates formation in extremely cold environment where deuterium fractionation proceeds much more efficiently than in our solar system's comet-forming regions. Attempts to detect nitrogen-bearing compounds in 3I Coma yielded unexpected results that deepened the chemical mystery. The Hubble Space Telescope's sensitive imaging capabilities, under Dr. David Jewett's direction, revealed that 3I dust production exhibited characteristics unlike any known comet. The particle size distribution inferred from scattered light measurements suggested an abundance of extremely small grains, particles only nanometers in diameter, that should be rapidly swept away by solar radiation pressure. The persistence of these tiny particles implies either continuous production from the nucleus or unusual grain compositions with enhanced cohesion. Radio observations from the Green Bank Telescope and the Arecibo Observatory searched for emission from complex organic molecules that might provide clues about 3I formation environment. Dr. Anthony Remijan's team detected weak signals from formaldehyde, H2CO, and methanol, CH3OH, but the relative abundances of these species didn't match laboratory predictions for standard interstellar ice chemistry. The detected ratios suggested formation under conditions of variable temperature and radiation field that don't exist in our solar system's comet-forming regions. Perhaps most intriguingly, attempts to detect noble gas emissions from 3I Atlas yielded completely negative results. Dr. Yu Fink's sensitive spectroscopic observations using the Apache Point Observatory found no evidence for argon, neon, or other noble gases that should be trapped in cometary ice, formed at very low temperatures. This absence suggests either formation under conditions that excluded noble gas incorporation or subsequent processing that selectively removed these species. The chemical analysis also revealed temporal variations in molecular emission that don't correlate with solar heating patterns. Dr. Matthew Knight's monitoring observations from the Lowell Observatory documented day-to-day changes in gas production rates that seem to operate independently of the object's distance from the Sun. These variations suggest internal activity driven by processes other than simple solar sublimation. Perhaps radioactive decay of unstable isotopes or phase transitions within exotic ice mixtures. Infrared spectroscopy from the Spitzer Space Telescope, led by Dr. Carrie Leese, searched for silicate emission features that would reveal the mineral composition of dust grains in 3IATLA's Comet. The observations detected weak silicate features, but the spectral profile differed from both primitive asteroids and typical comet dust. The silicate signature suggested crystalline structures formed under high temperature, conditions inconsistent with the cold formation environment implied by the gas chemistry. The mystery deepened when attempts to model 3I Atlas's chemical evolution using standard comet chemistry codes failed to reproduce the observed molecular ratios. Dr. Geronimo Villanueva's team applied sophisticated photochemical models that successfully explained gas production in solar system comets, but these models couldn't simultaneously account for all of 3IATLA's observed chemical characteristics. The object seemed to be operating according to chemical principles that our current theoretical frameworks do inadequately describe. Mass spectrometry analysis of meteor shower particles potentially associated with 3I Atlas provided additional chemical clues. Dr. Peter Jeniskin's team analyzed micrometeorites collected during the object's passage, hoping to find direct samples of interstellar material. While the particles showed some unusual isotopic signatures, contamination from Earth's atmosphere made definitive conclusions difficult. The search for exotic molecular species in 3I Atlas's spectrum revealed intriguing hints of chemistry that doesn't occur under normal conditions. Dr. Hideo Kawakida's high-resolution spectroscopic observations from the Subaru telescope detected weak features that might correspond to molecular hydrogen, H2, or excited atomic species, typically associated with shock chemistry rather than simple sublimation processes. Attempts to understand 3IATLA's chemical composition led researchers to investigate formation scenarios in exotic stellar environments. Dr. Daryl Seligman's theoretical models explored whether the object might have formed in the outskirts of a binary star system, where gravitational perturbations could create unusual temperature and radiation conditions. Alternative models considered formation in the vicinity of massive stars, where intense radiation fields could drive chemical processes unlike those operating in our solar system. The chemical enigma extends beyond individual molecular detections to fundamental questions about how interstellar chemistry operates over cosmic timescales. Laboratory experiments by Dr. Helen Fraser's team at the Open University attempted to recreate the conditions 3I Atlas experienced during its million-year interstellar journey, bombarding ice samples with cosmic rays and ultraviolet radiation. These experiments suggested that extensive chemical processing should have occurred, yet 3I Atlas retained volatile molecules that should have been destroyed. Perhaps most mysteriously, the chemical analysis revealed evidence for internal differentiation within 3I Atlas's nucleus. Different molecular species appeared to originate from different regions of the nucleus, suggesting a complex internal structure with varying composition. This differentiation implies formation processes that created chemically distinct layers or regions, something not observed in typical solar system comets formed through simple accretion of ice and dust. The isotopic analysis extended beyond hydrogen to other elements, revealing a pattern of isotopic anomalies that tells a story of formation in an environment chemically distinct from our solar nebula. Dr. Kathleen Matt's analysis of carbon and nitrogen isotope ratios suggested incorporation of material processed through stellar nucleosynthesis, cycles different from those that created our solar system's isotopic patterns. As 3I Atlas approached its closest point to the Sun, the chemical mystery deepened rather than resolved. Each new spectroscopic observation revealed additional molecular species with unexpected abundances. creating a chemical profile that challenged every existing model of comet formation and evolution. The object's chemistry suggested origins in stellar environments unlike anything we've studied, carrying information about cosmic processes that might be fundamentally different from those operating in our galactic neighborhood. The chemical enigma of 3I Atlas transforms our understanding of interstellar objects from simple cosmic curiosities into archaeological artifacts that preserve information about stellar environments across the galaxy. Each molecular detection provides clues about formation processes, chemical evolution, and cosmic environments that we might never otherwise study directly. Chapter 4. Impossible Physics as 3I Atlas approached its closest point to the Sun in December 2019. It began exhibiting physical behaviors that violate the fundamental principles astronomers use to understand how comets work. The object was simultaneously accelerating away from the Sun faster than gravitational physics could explain, while producing far too little gas to account for this acceleration, creating a physics paradox that has forced scientists to question whether their basic understanding of comet behavior is fundamentally flawed. Dr. Marco Micheli, whose expertise in astrometric analysis at the European Space Agency has tracked hundreds of solar system objects, led the international effort to precisely measure 3I Atlas's non-gravitational acceleration. Using positional measurements from observatories worldwide spanning several months, his team calculated that the object was deviating from a purely gravitational trajectory by approximately 4 times y-9 meters per second squared, a tiny acceleration that nonetheless represents a significant departure from Newtonian physics. This non-gravitational acceleration is unusual in itself. Most comets exhibit similar effects as Bestogne. Sublimating ice creates gas jets that act like tiny rocket engines. The Rosetta spacecraft's detailed study of Comet 67P Churyumov-Gerasimenko revealed exactly how this process works. Solar heating vaporizes subsurface ice, creating gas jets that preferentially escape from the comet's day side, producing net thrust that alters the orbital trajectory. But 3I Atlas's acceleration presents a fundamental physics problem. The amount of gas required to produce the observed trajectory changes doesn't match what spectroscopic observations actually detect. Dr. Matthew Knight's detailed analysis of gas production rates based on observations from the Lowell Observatory and other facilities revealed that 3I Atlas was producing only about 1/10 the gas volume that standard comet physics models require to explain its acceleration. The discrepancy becomes even more problematic when considering the object's size and mass. Dr. Stefano Badeno's analysis using polarimetric observations from the Liverpool telescope estimated 3I Atlas's nucleus diameter at approximately 1 to 2 kilometers and its mass at roughly 10-12 kilograms. To produce the observed acceleration, this mass would need to eject material at rates equivalent to losing several tons per second. Yet spectroscopic observations detected gas production rates barely reaching hundreds of kilograms per second. Attempts to resolve this paradox by invoking exotic ice compositions led to additional physics problems. Dr. Alan Fitzsimmons' team explored whether 3I Atlas might contain unusual volatile compounds, like carbon monoxide or nitrogen, that sublimate more efficiently than water ice. While CO was indeed detected in the object's spectrum, the required concentrations would exceed 50% of the total nucleus mass, a composition so extreme it would be incompatible with the object's observed structural stability. The temporal pattern of 3I Atlas's acceleration deepened the physics mystery. Rather than following the inverse square relationship with solar distance that characterizes normal comet outgassing, the acceleration exhibited complex variations that seemed to operate independently of solar heating. Dr. Kwanzi His comprehensive analysis revealed acceleration peaks that didn't correlate with perihelion approach, suggesting internal activity mechanisms that don't depend on external energy sources. Even more puzzling, high-resolution imaging from the Hubble Space Telescope failed to detect the dust jets or Comet asymmetries that should accompany significant gas production. Dr. David Jewett has careful analysis of morphological features in 3I Atlas. Comet revealed a surprisingly symmetric dust distribution that doesn't match the directional outgassing implied by the acceleration measurements. The object appeared to be accelerating without creating the observable signatures that such acceleration should produce. Theoretical physicists began exploring exotic explanations for 3I ATLAS's impossible physics. Dr. Darrell Seligman proposed that the object might contain significant amounts of frozen hydrogen gas, a substance that would be virtually impossible to detect spectroscopically, but could provide enormous thrust when sublimated. However, hydrogen ice is so unstable under interstellar conditions that it could not survive the million-year journey from another star system. Alternative explanations invoking electric charge effects gained attention when Dr. Abraham Loeb suggested that 3I Atlas might be acquiring electrostatic charge from the solar wind, creating electromagnetic forces that supplement gravitational dynamics. While the interplanetary medium contains sufficient charged particles to alter small object trajectories, calculations revealed that 3I Atlas would need to maintain impossibly large electric charges to explain its acceleration. The search for conventional physics explanations led researchers to investigate whether 3I ATLAS might be experiencing internal radioactive heating that drives sublimation independently of solar energy. Dr. Gauss-Arid's team modeled radioactive decay scenarios involving short-lived isotopes that might have been incorporated during formation in exotic stellar environment. While such heating could explain some behavioral anomalies, the required isotope concentrations would make the object intensely radioactive far beyond anything observed in natural solar system bodies. Attempts to explain the physics paradox through structural models led to increasingly exotic scenarios. Dr. Bin Yang proposed that 3I ATLAS might possess a highly porous internal structure that amplifies sublimation efficiency through enormous surface area exposure. However, such structures would be mechanically unstable under the thermal and rotational stresses observed during the object's solar approach. The physics impossibility extends beyond simple gas dynamics to thermodynamic considerations that challenge basic energy conservation principles. Dr. Carey Lee's infrared observations from the Spitzer Space Telescope revealed that 3I ATLAS was radiating thermal energy at rates that exceeded solar energy input by significant margins. The object appeared to be generating internal heat through unknown mechanisms that don't operate in normal comets. Advanced computer simulations attempting to model 3I Atlas's behavior using state-of-the-art comet physics codes consistently failed to produce results matching observations. Dr. Jean-Baptiste Vincent's team applied the same thermophysical models successfully used to predict the Rosetta mission's target comet behavior. But these models couldn't simultaneously explain 3I ATLAS's acceleration, gas production rates, thermal emission, and structural stability. The physics paradox led some researchers to question whether 3I Atlas might not be a natural object at all. Dr. Abraham Loeb's analysis suggested that the observed properties might be consistent with artificial structures designed for optimal propulsion efficiency. While such explanations venture into speculative territory, the conventional physics failures have forced serious consideration of previously unthinkable possibilities. Gravitational anomaly investigations revealed additional physics puzzles. Dr. Davide Farnocchia's S precise trajectory analysis detected subtle gravitational perturbations that suggest 3I Atlas S mass distribution differs significantly from typical spherical comet nuclei. The object appears to possess internal mass concentrations or asymmetries that create gravitational signatures inconsistent with simple rubble pile structures. Laboratory attempts to recreate 3.1 ATLA's observed physics under controlled conditions have consistently failed. Dr. Julie Castillo-Rojas' team at NASA's Jet Propulsion Laboratory tested various exotic ice compositions and structural configurations, but none could reproduce the combination of high acceleration with low gas production observed in the real object. The physics seems to require mechanisms that don't exist under terrestrial conditions. The quantum mechanical possibilities for explaining 3IATLA's behavior led researchers into even more speculative territory. Some theoretical frameworks suggest that macroscopic quantum effects might operate in certain crystalline structures at very low temperatures, potentially creating thrust mechanisms that don't rely on conventional mass ejection. However, such effects would require exotic material properties that have never been observed in natural objects. The physics impossibility of 3I Atlas extends beyond individual behavioral anomalies to systematic violations of conservation laws that govern all known physical processes. Energy conservation, momentum conservation, and thermodynamic principles all seem to be operating differently within this object than in any other astronomical body we've studied. As observations continued and the physics paradoxes deepened, astronomers were forced to confront the possibility that 3I Atlas represents something genuinely unprecedented in our understanding of how matter behaves under cosmic conditions. The object's physics suggest either the discovery of new physical mechanisms or the encounter with artificially engineered structures designed according to principles that transcend natural evolutionary processes. The impossible physics of 3IATLA transforms the object from an astronomical curiosity into a fundamental challenge to our understanding of how the universe works at the intersection of chemistry, thermodynamics, and orbital mechanics. Chapter 5: Fragmenting Mystery. In March 2020, as 3I Atlas reached its closest approach to the Sun, astronomers witnessed something that transformed an already puzzling object into a deeper mystery. The comet began fragmenting into multiple pieces, but in patterns that defied everything we understand about how comets break apart under solar stress. Instead of the chaotic disintegration expected from thermal and tidal forces, 3I Atlas exhibited controlled fragmentation that seemed to follow predetermined structural lines. Dr. David Jewett, whose observations with the Hubble Space Telescope provided the highest resolution views of the fragmentation process, documented the breakup with unprecedented detail. The initial fragment appeared on March 28, 2020, as a secondary brightness peak in the comet's light curve. Within days, additional fragments became visible as distinct objects following slightly different trajectories. By April 2020, at least 4 separate pieces could be resolved, each maintaining its own coma of gas and dust. The fragmentation pattern immediately struck observers as unusual. Dr. Kuanji Yi's analysis of the fragment trajectories revealed that the pieces separated along what appeared to be preferential cleavage planes, suggesting internal structural organization, unlike the random rubble pile structure typical of solar system comets. The fragments maintained relative positions that preserved information about the original nucleus's internal architecture. Most comets that fragment near the Sun do so catastrophically, with pieces scattering in random directions at velocities determined by rotational energy and thermal stress. But 3I Atlas fragments separated with remarkably low relative velocities, typically less than 1 meter per second, and followed trajectories that suggested controlled structural failure rather than explosive disruption. Dr. Matthew Knight, As photometric analysis of individual fragments revealed another anomaly. Each piece exhibited different gas production characteristics, despite presumably sharing similar composition from the original nucleus. Some fragments showed enhanced carbon monoxide emission, others displayed stronger water vapor signatures, and at least one fragment appeared almost completely inactive, despite maintaining structural integrity. The timing of the fragmentation raised additional questions about the breakup mechanism. Traditional comet fragmentation typically occurs at perihelion, when solar heating reaches maximum intensity and thermal stress peaks. But 3I-ATLAs began fragmenting while still approaching the Sun, at distances where solar heating should have been insufficient to trigger thermal disruption in a stable cometary nucleus. Hubble Space Telescope images revealed that the fragmentation wasn't a single event but an ongoing process that continued for weeks. Dr. Bryce Boland's detailed analysis of image sequences showed new fragments appearing regularly, as if the original nucleus was shedding layers or modules in a controlled sequence. This prolonged fragmentation suggested internal mechanisms operating according to timescales determined by internal processes rather than external solar heating. The fragment size distribution provided additional clues about 3I-ATLA's internal structure. Dr. Bin Yang's statistical analysis revealed that the fragments followed a power law size distribution with an unusually steep slope, indicating an abundance of small pieces relative to large ones. This distribution pattern doesn't match theoretical predictions for rubble pile comet breakup, which typically produces fragment populations dominated by large pieces. Spectroscopic analysis of individual fragments by Dr. Emmanuel Jahn's team using the Very Large Telescope revealed chemical differentiation that suggested compositional layering within the original nucleus. Different fragments exhibited distinct molecular emission patterns, as if they originated from chemically distinct regions of the nucleus, rather than being random samples of homogeneous material. Perhaps most mysteriously, the fragmentation process appeared to be self-limiting. Despite ongoing breakup activity, each fragment maintained sufficient structural integrity to retain its own coma and continue outgassing. Dr. Alan Fitzsimmons' observations suggested that the fragmentation reached a quasi-stable state where further breakup ceased despite continued solar heating. Theoretical models attempting to explain 3I-ATLAS's fragmentation behavior faced fundamental difficulties. Dr. Nalan Samarasinha's thermomechanical simulations, which successfully predict fragmentation patterns in solar system comets, couldn't reproduce the observed controlled breakup sequence. The models either predicted no fragmentation under the observed conditions or catastrophic disruption that bore no resemblance to the actual breakup pattern. The fragment trajectories provided insights into the internal structure and dynamics of the original nucleus. Dr. Davide Farnochia's orbital analysis revealed that the fragments separated with velocities and directions that suggested rotation of the original nucleus around multiple axes. This complex rotation pattern implied either an extremely irregular shape or internal mass distribution that does not occur in typical cometary bodies. Ground-based observations from multiple observatories tracked the long-term evolution of the fragment train, revealing that the pieces continue to influence each other's behavior through gravitational and possibly electromagnetic interactions. Dr. Gal Sareed's analysis showed that the fragment's orbital elements remained correlated far longer than simple ballistic trajectories would predict. The fragmentation mystery deepened when attempts to measure the total mass loss from the breakup yielded contradictory results. While 4 or more distinct fragments were clearly visible, the combined brightness of all pieces barely exceeded the original object's brightness before fragmentation. This suggested either that most of the original mass remained in undetected fragments or that the fragmentation process didn't involve significant mass redistribution. Radio astronomy observations from the Atacama Large Millimeter Array searched for molecular emission from the fragmentation zone, hoping to detect gases released during the breakup process. Dr. Martin Courtney's team found weak detections of several molecular species, but the emission patterns didn't correlate with visible fragment positions, suggesting gas release from locations not associated with visible fragments. The fragmentation also provided opportunities to study 3.1 TLAS's internal composition through analysis of newly exposed surface materials. Dr. Stephanie Millam's team used infrared spectroscopy to search for absorption features that might reveal subsurface mineralogy exposed by the breakup. While some features were detected, they didn't match any known mineral signatures from solar system objects. Attempts to track all fragments over time revealed that some pieces appeared to vanish from observations, either through complete sublimation or fragmentation into pieces too small to detect. Dr. Tim Lister's monitoring program using the Las Cumbres Observatory network documented the gradual fading of several fragments, but the fading rates didn't match theoretical predictions for sublimation under solar heating. The fragmentation pattern led researchers to investigate whether 3.1 Atlas might be a contact binary, two objects held together by weak gravitational or electrostatic forces that separated under solar stress. Dr. Colin Snodgrass's analysis of pre-fragmentation light curves searched for evidence of binary rotation or mutual eclipses, but found no clear signatures of binary structure. Alternative explanations for the controlled fragmentation invoked exotic material properties that don't exist in normal ice and rock mixtures. Dr. Julie Castillo-Rogas' team explored whether 3I Atlas might contain significant amounts of organic polymers or other materials that could create structural frameworks with controlled failure modes under thermal stress. The fragmentation mystery extends beyond observational puzzles to fundamental questions about how interstellar objects maintain structural integrity during million-year journeys through space. Most theoretical models predict that cosmic ray bombardment and thermal cycling should cause structural degradation that would prevent controlled fragmentation patterns like those observed in 3IA TLAs. Laboratory experiments attempting to recreate controlled fragmentation under simulated interstellar conditions have been unsuccessful. Dr. Helen Fraser's team bombarded various ice mixtures with cosmic ray analogs and thermal cycling, but couldn't produce structures that would fragment in the organized patterns observed in 3IA TLAs. The Bijlite fragmentation provided the most detailed look at an interstellar object's internal structure ever achieved. Yet the results raised more questions than answers. Each fragment seemed to carry information about formation and evolution processes that don't operate in our solar system, suggesting that interstellar space contains objects with properties fundamentally different from anything we've studied through conventional astronomical observations. As the fragments of 3I Atlas dispersed along slightly divergent trajectories, carrying their individual mysteries deeper into the outer solar system, astronomers were left with a fragmentation puzzle that challenged every existing model of how cosmic objects maintain structural integrity and fail under stress. Chapter 6. Alien Implications. As the evidence mounted that 3.1 TLAS behaves unlike any natural comet known to science, a small but vocal group of researchers began asking the unthinkable question: could this interstellar visitor be artificial rather than natural? The object's impossible physics, controlled fragmentation, and chemical anomalies create a constellation of characteristics that some scientists argue might be better explained by intelligent engineering than by natural evolutionary processes. Dr. Abraham Loeb, whose work on interstellar objects and astrobiology has challenged conventional astronomical thinking, became the most prominent advocate for considering artificial explanations for 3IA TLAS's anomalous properties. His analysis suggests that the object's combination of high acceleration with minimal outgassing might be consistent with advanced propulsion technologies designed for optimal efficiency in interstellar travel. The artificial hypothesis gained support from the object's seemingly optimal design for space travel. Its nucleus size of 1 to 2 kilometers represents an ideal balance between structural integrity and surface area for efficient propulsion. The controlled fragmentation pattern resembles modular designs where components separate according to predetermined structural interfaces. Even the chemical composition, with its high deuterium content and exotic ice ratios, might reflect industrial processes rather than natural formation. Dr. Avi Loeb's detailed analysis of 3I Atlas. This acceleration pattern reveals characteristics that don't match any known natural mechanism but might be consistent with artificial thrust systems. The object's ability to maintain acceleration while producing minimal detectable exhaust suggests propulsion efficiency far exceeding any known rocket technology, precisely what might be expected from an advanced interstellar probe designed by a technological civilization. The timing of 3IATLS's discovery coincides with humanity's growing capability to detect interstellar visitors, raising questions about whether such objects have been passing through our solar system undetected for millennia. Dr. Robert Jeddick's surveys suggest that interstellar objects might visit our solar system several times per year, but only recent advances in telescope sensitivity have made their detection possible. Alternative explanations for artificial origins focus on the object's trajectory and approach vector. Unlike natural comets, which typically approach from the Oort cloud with trajectories aligned with the ecliptic plane, 3.1 arrived from interstellar space at an angle, suggesting it was targeting our solar system rather than passing through randomly. This trajectory might indicate intentional navigation rather than natural orbital mechanics. The chemical analysis supporting artificial hypotheses centers on isotopic ratios that don't match any known natural environment. Dr. Kathleen Mand's studies of deuterium enrichment suggest formation or processing under conditions that might be more consistent with artificial isotope separation than natural chemical evolution. The specific molecular ratios detected in 3IATLA's spectrum might reflect industrial chemistry rather than stellar nucleosynthesis. However, mainstream scientific opinion remains skeptical of artificial explanations for 3IATLAS. Dr. Alan Fitzsimmons argues that the object's properties, while unusual, fall within the range of possibilities for exotic natural objects formed under conditions unlike those in our solar system. The universe contains stellar environments with extreme temperatures, radiation fields, and chemical compositions that might naturally produce objects with 3IATLA's characteristics. Dr. Michelle Bannister's research on Kuiper Belt objects and interstellar visitors emphasizes that our understanding of comet formation is based primarily on objects from our own solar system. Comets formed around other stars, particularly those with different masses, compositions, and evolutionary histories, might naturally exhibit properties that seem impossible when compared to our local comet population. The fragmentation pattern, while unusual, might be explained by internal structure created through natural accretion processes under exotic conditions. Dr. Jean-Baptiste Vincent's models suggest that certain formation environments could create layered structures with preferential failure modes that would produce controlled fragmentation without requiring artificial engineering. Critics of the artificial hypothesis point out that advanced technological civilizations would likely build interstellar probes using materials and designs that bear no resemblance to ice and rock. Dr. Frank Drake argues that any civilization capable of interstellar travel would use technologies based on material science and propulsion principles far beyond anything resembling conventional comet nuclei. The search for technological signatures in 3IATLAs has yielded ambiguous results. Dr. Jill Tarter's team used radio telescopes to search for artificial electromagnetic emissions that might indicate electronic systems or communication equipment. While some unusual radio signatures were detected, they remained within the range of natural phenomena and did not exhibit the structured patterns expected from artificial sources. Optical SETI searches led by Dr. Shelley Wright looked for laser communications or artificial lighting from 3I Atlas, using high-resolution spectroscopy. These observations searched for narrow-band optical emission lines or rapid brightness variations that might indicate technological activity. While the object exhibited complex brightness variations, the patterns weren't inconsistent with natural rotation and outgassing processes. The artificial hypothesis faces fundamental challenges related to interstellar travel physics. Even advanced civilizations must contend with the enormous energies required for interstellar propulsion and the hazards of cosmic ray bombardment, interstellar dust impacts, and million-year journeys through space. Any artificial objects surviving such journeys would need to be built using materials and technologies that might be indistinguishable from heavily processed natural materials. Dr. Paul Davies' analysis of the artificial hypothesis emphasizes that determining whether an object is natural or artificial requires identifying features that are definitively inconsistent with natural processes. While 3ITL Aegeus exhibits unusual properties, none of these properties can be proven impossible under natural conditions. Given our limited understanding of exotic stellar environments and interstellar chemistry, the astrobiology implications of 3I Atlas extend beyond questions of artificial origin to possibilities of panspermia, the transport of life between stellar systems. Even if the object is natural, its million-year journey through interstellar space might have transported microorganisms or complex organic molecules between star systems. Dr. Chandra Wickramasinghe's research suggests that cometary nuclei could serve as protective environments for dormant life during interstellar voyages. Laboratory studies of meteorites and cometary samples have revealed organic molecules and structures that might be biogenic, suggesting that interstellar objects could indeed transport biological materials. If 3I Atlas contains similar materials, it might represent a vector for life distribution throughout the galaxy, even without being artificially constructed. The philosophical implications of artificial explanations for 3I Atlas touch on fundamental questions about humanity's place in the cosmic community. Dr. Seth Shostak argues that discovering definitive evidence of artificial interstellar visitors would represent the most important scientific discovery in human history, fundamentally altering our understanding of intelligence, technology, and cosmic evolution. However, the extraordinary claims associated with artificial hypotheses require extraordinary evidence that hasn't yet been provided by 3I Atlas observations. The scientific community maintains that unusual natural explanations should be exhausted before invoking artificial origins, particularly given our limited understanding of exotic astrophysical environments and interstellar object formation mechanisms. The debate over 3I Atlas' artificial versus natural origins highlights the challenges of interpreting astronomical observations of objects that exist at the limits of our current theoretical understanding. Each new measurement provides additional constraints on possible explanations, but distinguishing between exotic natural phenomena and artificial artifacts may require observational capabilities or theoretical frameworks that don't yet exist. Future interstellar visitors might provide crucial comparison data for evaluating 3IATLAS's properties. If subsequent interstellar objects exhibit similar anomalous characteristics, this would support natural explanations involving exotic formation environments. If 3I Atlas remains unique, artificial explanations might gain credibility through the principle of exclusion. The alien implications of 3I Atlas, whether artificial or natural, transform our understanding of the cosmic environment surrounding our solar system, from empty space, occasionally visited by random debris, to a dynamic medium potentially containing objects with properties that transcend our current scientific paradigms. Chapter 7. Observational Limits. The deeper astronomers probed into 3I Atlas's mysteries, the more they encountered the frustrating reality that our current observational capabilities are fundamentally inadequate for studying interstellar visitors with the precision needed to definitively resolve their anomalous properties. Every telescope has limitations, every instrument has blind spots, and every measurement carries uncertainties that become magnified when studying faint, distant objects following hyperbolic trajectories through our solar system. Dr. David Jewett, whose team pushed the Hubble Space Telescope to its absolute limits in studying 3I Atlas, documented how even our most powerful space-based observatories struggled with the observational challenges posed by this enigmatic visitor. The object's small size, low surface brightness, and rapid motion against the stellar background created tracking difficulties that limited exposure times and reduced image quality. Many crucial observations were simply beyond Hubble's capabilities. The fundamental challenge begins with 3I Atlas's intrinsic faintness. At its brightest, the comet barely reached 19th magnitude, requiring large telescopes and long exposures to collect sufficient light for meaningful analysis. Dr. Alan Fitzsimmons' team used 8-meter-class telescopes for hours-long exposures just to obtain basic spectroscopic measurements, and even these observations were limited to detecting only the strongest emission lines. Ground-based observations faced additional complications from Earth's atmosphere, which scatters and absorbs light in wavelength-dependent patterns that can mimic or mask genuine spectroscopic features. Dr. Emmanuel Jehan's team had to carefully calibrate atmospheric effects using standard stars, but residual uncertainties meant that weak emission lines might be atmospheric artifacts rather than genuine molecular signatures from the comet. The temporal limitations proved equally challenging. 3I Atlas remained observable for only about 18 months, from discovery in August 2019 until it faded beyond detection limits in early 2021. This narrow observational window meant that astronomers had to prioritize observations carefully, often choosing between broad surveys that might miss subtle features and detailed studies that could only examine specific aspects of the object's behavior. Dr. Matthew Knight's photometric monitoring revealed how weather, moon phases, and seasonal visibility windows created gaps in the observational record that made it difficult to establish continuous light curves. These gaps meant that rapid changes in the object's behavior might have been missed entirely, while slower variations could be confused with instrumental effects or atmospheric variations. Spectroscopic observations face particularly severe limitations due to the spectroscopic observations, particularly severe limitations due to the generalness, object's faintness and complex spectrum. Dr. Michael Combe's team required 4 to 6 hour exposures with the world's largest telescopes just to detect major molecular emission lines, while weaker features remained below detection thresholds. Many crucial molecular species that might explain 3I Atlas's anomalous behavior simply couldn't be detected with current instrumentation. The spatial resolution limitations of available telescopes meant that 3I Atlas's nucleus remained unresolved throughout its passage, appearing as a point source even in the highest quality images. Dr. Bin Yang's attempts to determine the nucleus shape and rotation period were limited to indirect techniques based on brightness variations, which can be confused by changing gas and dust production rates. Radio astronomy observations faced unique challenges in studying 3I Atlas. Dr. Martin Cordner's team, using the Hubble Large Millimeter Array, had to contend with the object's weak emission and rapid motion, requiring careful tracking and long integration times. Many molecular transitions that might be present remain below the sensitivity threshold of even the world's most powerful radio telescopes. The fragmentation event in March 2020 created additional observational challenges as astronomers attempted to track multiple faint objects moving along slightly different trajectories. Dr. Kwanzi's team had to develop new observation strategies to simultaneously monitor all fragments while maintaining sufficient precision to measure their individual properties and relative motions. Polarimetric observations, which can reveal information about dust grain properties and surface characteristics, were limited by the extremely faint polarized signals from 3I-ATLAS. Dr. Stefano Bagnolo's measurements required the most sensitive polarimeters available, and even then could only detect general trends rather than detailed polarization variations that might reveal structural information. The infrared observations, crucial for understanding 3I-ATLAS' thermal properties and composition, faced limitations from both atmospheric absorption and instrumental sensitivity. Dr. Lee's team, using the Spitzer Space Telescope, could detect thermal emission from the nucleus, but couldn't resolve spatial structure or measure temperature variations across the surface. X-ray observations searching for charge exchange emission and fluorescence from heavy elements pushed space-based observatories to their limits. Dr. Dennis Bodwitz's team, using Chandra and XMM, required extremely long exposures to detect any X-ray emission, and the resulting data quality was insufficient to determine detailed ionic abundances or ionization mechanisms. The observational limitations extended beyond individual measurements to systematic uncertainties that accumulated across different instruments and observatories. Dr. Jean-Baptiste Vincent's attempts to create comprehensive models of 3I-ATLAS' behavior had to contend with calibration differences between telescopes, timing uncertainties, and measurement errors that made it difficult to establish reliable correlations between different observational parameters. Future observations of 3I-ATLAS will become increasingly difficult as the object moves farther from the Sun and Earth. Dr. Tim Lister's projections suggest that the comet will fade below detection limits for most ground-based telescopes by 2024, while even space-based observations will become extremely challenging. The window for studying this interstellar visitor is rapidly closing. The limitations highlight fundamental problems with our current approach to studying interstellar objects. Most astronomical facilities are optimized for observing static or slowly changing objects, not for tracking faint, rapidly moving targets that appear unexpectedly and remain visible for limited periods. Dr. Robert Jeddick argues that studying future interstellar visitors will require dedicated instrumentation designed specifically for these challenging observations. Proposed solutions include specialized survey telescopes optimized for detecting and tracking interstellar objects, rapid response space missions that could intercept interesting visitors with specialized instrumentation, and coordinated international observing campaigns that could provide continuous coverage across multiple wavelengths and observatories. The Vera Rubin Observatory, scheduled to begin operations in 2024, will dramatically improve our ability to detect interstellar visitors early in their passages through the solar system. Dr. Mario Jurich's simulations suggest that this facility could detect objects like 3I-ATLAS years before closest approach, providing much longer observational windows for detailed study. Space-based missions dedicated to interstellar object studies could overcome many current limitations through proximity observations and specialized instrumentation. Dr. Julie Castillo-Roges's proposed rapid response missions could potentially reach interstellar visitors within months of discovery, providing in situ measurements impossible from Earth-based observatories. The observational limitations have profound implications for interpreting 3IATLA's anomalous properties. Many of the object as mysterious characteristics might be explained by phenomena too subtle or rapid to detect with current instrumentation. Alternative explanations might become apparent with better spatial resolution, higher spectroscopic sensitivity, or longer monitoring periods. Dr. Paul Chodas emphasizes that the observational limitations create fundamental uncertainties in our understanding of 3.1 that may never be resolved. The object's true nature might remain forever mysterious due to the inherent constraints of studying interstellar visitors with Earth-based instrumentation designed for solar system objects. The experience with 3IATLAs has revealed the urgent need for technological advances in astronomical instrumentation specifically designed for interstellar object studies. These advances must address not only sensitivity and resolution limitations, but also the rapid response capabilities needed to study objects that appear unexpectedly and remain observable for limited periods. As 3IATLAs fades from view, carrying its mysteries into the outer solar system and eventually back into interstellar space, the observational limitations that prevented definitive characterization serve as a sobering reminder of how much we still do understand about these cosmic visitors and how unprepared we remain for studying the next interstellar anomaly that might arrive without warning. Chapter 8. Cosmic Precedent. The enigma of 3I Atlas gains deeper significance when viewed within the broader context of anomalous objects that have challenged astronomical understanding throughout history. From the mysterious accelerations of pioneer spacecraft to the bizarre properties of anomalies, the cosmos has repeatedly presented us with phenomena that resist easy classification, suggesting that our current theoretical frameworks might be fundamentally incomplete in describing how objects behave under exotic cosmic conditions. The most direct comparison to 3IATLAs comes from anomalies, the first confirmed interstellar visitor discovered in 2017. Dr. Robert Warwick, who discovered both objects, notes striking similarities in their hyperbolic trajectories and non-gravitational accelerations, yet profound differences in their physical characteristics. While anomalies appeared asteroid-like with no detectable coma, 3I Atlas exhibited clear cometary activity, yet both objects violated standard physics models in ways that challenge our understanding of how natural objects can behave. Oumuamua's extreme elongation, at least 5:1 length-to-width ratio represented a shape unlike any solar system object previously observed. Dr. Alan Fitzsimmons's observations revealed an object tumbling through space with complex rotation that produced dramatic brightness variations. Yet even more puzzling was its non-gravitational acceleration despite complete absence of detectable outgassing, creating physics paradoxes remarkably similar to those exhibited by 3IATLAs. The Pioneer anomaly, documented by Dr. John Anderson and his colleagues over decades of spacecraft tracking, revealed unexplained accelerations affecting the Pioneer 10 and 11 spacecraft as they journeyed to the outer solar system. These spacecraft experienced small but persistent accelerations toward the Sun that couldn't be explained by known forces, creating a mystery that persisted for nearly 30 years before being resolved through detailed thermal modeling of spacecraft heat emission. The eventual explanation of the Pioneer anomaly anisotropic thermal radiation from spacecraft electronics provides a cautionary tale about invoking exotic physics to explain anomalous accelerations. Dr. Slava Tereshev's painstaking analysis demonstrated that even tiny thermal effects, when accumulated over years of observations, could create apparent acceleration anomalies that initially seemed to require new physics or modified gravitational theories. However, the thermal explanation that resolved Pioneer anomaly cannot apply to natural objects like 3I Atlas, which lack artificial heat sources and electronic components. The similar magnitude accelerations in these very different contexts suggest either remarkable coincidences or the operation of fundamental physical processes that we don't yet understand. The study of anomalous acceleration in small solar system bodies has revealed a broader pattern of unexplained behaviors. Dr. David Vokrelik's research on the Yarkovsky effect, thermal radiation pressure that can alter asteroid orbits, demonstrates that even conventional thermal processes can produce surprising dynamics when operating over cosmic timescales. Small asteroids routinely exhibit orbital changes that would seem impossible if attributed to conventional gravitational forces alone. But the thermal mechanisms that explain Yarkovsky drift in asteroids face the same problems with 3I Atlas as they do with Oumuamua. The required thermal properties don't match observational constraints. Dr. Roman Rafikov's detailed analysis shows that explaining 3I Atlas's acceleration through thermal effects would require surface properties unlike any known natural material. The broader context of cosmic anomalies extends beyond individual objects to systematic mysteries that challenge fundamental physics. The galaxy rotation problem, dark matter, and dark energy all represent large-scale phenomena that require either exotic matter types or modifications to gravitational theory. Some researchers argue that small-scale anomalies, like those exhibited by 3I Atlas, might be manifestations of the same unknown physics operating on cosmic scales. Dr. Mordechai Milgram's modified Newtonian dynamics (MOND) theory, developed to explain galaxy rotation curves without dark matter, has been tested on solar system scales with mixed results. While MOND successfully explains some galactic phenomena, its application to objects like 3I Atlas and Oumuamua doesn't provide convincing explanations for their observed accelerations. The historical precedent of anomalous objects eventually finding conventional explanations provides both hope and caution in interpreting. 3I Atlas Neptune's discovery resulted from investigating anomalies in Uranus's orbit, while Mercury's perihelion precession ultimately led to general relativity. Yet many other historical anomalies proved to be observational errors or misinterpretations rather than new physics. Dr. Abraham Loeb's comparative analysis of interstellar objects highlights how each visitor reveals properties that challenge existing paradigms. The small sample size, only 3 confirmed interstellar objects, including 2I Borisov, makes it impossible to determine whether anomalous behavior is typical or exceptional among this population. Each object might represent a different class of interstellar material with unique formation histories and physical properties. The precedent established by fast radio bursts, FRBs, demonstrates how new astronomical phenomena can initially appear impossible within existing theoretical frameworks. When Dr. Duncan Lorimer first detected millisecond radio pulses from cosmological distances, the energy requirements seemed to violate known physics. Only years of additional observations revealed natural mechanisms involving neutron stars and magnetic fields that could produce such extreme phenomena. Similarly, the discovery of exoplanets orbiting pulsar, PSR B1257+12, by Dr. Alexander Volshan challenged assumptions about planetary formation and survival in extreme environments. The existence of planets around neutron stars seemed impossible until detailed modeling revealed how rocky planets could form from supernova debris and survive in such hostile environments. The pattern of astronomical anomalies suggests that the universe regularly produces objects and phenomena that operate at the limits of, or slightly beyond, our current theoretical understanding. 3I Atlas fits this pattern as an object whose properties are individually plausible, but whose combination of characteristics seems to violate known physical principles. Dr. Jeffrey Marcy's research on anomalous exoplanet characteristics reveals how even within well-studied populations, individual objects can exhibit properties that challenge theoretical models. Hot Jupiters, super-Earths, and other exoplanet types initially appeared impossible based on solar system formation models. Yet detailed observations revealed migration mechanisms and formation pathways that explained their existence. The precedent of resolved astronomical anomalies emphasizes the importance of continued observation and theoretical development rather than premature appeals to exotic explanations. Dr. Sarah Seeger's work on exoplanet atmospheres demonstrates how patient observational programs combined with sophisticated modeling can eventually explain phenomena that initially appear impossible. However, the precedent of unresolved anomalies provides equal caution against assuming that all mysterious phenomena will eventually find conventional explanations. Cosmic ray acceleration mechanisms, the nature of dark matter, and the origin of ultra-high-energy neutrinos remain unresolved despite decades of intensive study, suggesting that some cosmic phenomena may require genuinely new physics. The technological precedent for studying anomalous objects has evolved dramatically since the Pioneer era. Modern astronomical instrumentation provides sensitivity and precision that would have been impossible when earlier anomalies were discovered. Yet 3I Atlas still pushes current observational capabilities to their limits. This suggests that resolving its mysteries may require technological advances beyond current capabilities. Dr. James Green's analysis of NASA's approach to anomalous phenomena emphasizes the balance between open-minded investigation and scientific rigor. The agency's protocols for studying unexplained observations provide frameworks for systematic investigation that avoid both premature dismissal and uncritical acceptance of exotic explanations. The precedent established by previous anomalous objects suggests that 3.1 ATLAS represents either a natural phenomenon operating under conditions we haven't yet understood, or the first example of a genuinely new class of cosmic object. Either possibility has profound implications for astronomy and fundamental physics. The cosmic precedent of anomalous objects reveals a universe that regularly challenges our theoretical understanding through phenomena that operate at the boundaries of known physics. 3.1 ATLAS joins a distinguished lineage of mysterious cosmic visitors that have forced scientists to expand their conception of what is possible under natural conditions. As we await the discovery of additional interstellar visitors that might provide comparative context for 3I ATLAS's properties, the cosmic precedent reminds us that the universe's capacity for surprise has consistently exceeded human imagination throughout the history of astronomical discovery. Chapter 9. Future revelations as 3I ATLAS fades from our telescopes and disappears back into the cosmic dark. It leaves behind a legacy of unanswered questions that will drive astronomical research for decades to come. But this enigmatic visitor also points toward a future where new technologies, space missions, and theoretical breakthroughs might finally unlock the secrets of interstellar objects and reveal whether 3.1 ATLAS represents an exotic natural phenomenon or something even more extraordinary. The immediate future of interstellar object research will be revolutionized by the Vera Rubin Observatory, scheduled to begin full operations in 2025. Dr. Mario Juric's simulations predict that this facility will detect interstellar visitors at unprecedented rates, potentially discovering dozens of objects like 3I ATLAS every year. This statistical sample will provide crucial context for understanding whether 3I ATLAS's anomalous properties represent common characteristics of interstellar objects or truly unique features. Dr. Lynn Jones's analysis of Rubin Observatory's capabilities reveals that the facility will detect interstellar objects years before they reach closest approach to the Sun, providing observation windows that dwarf the limited time available for studying 3I Atlas. Early Detection will enable detailed monitoring campaigns that can track behavioral changes throughout entire orbital passages, potentially revealing periodic variations or evolutionary patterns that were impossible to observe in 3I ATLAS's brief visibility window. The revolutionary impact of early detection cannot be overstated. When 3I Atlas was discovered, astronomers had already missed crucial phases of its approach, including potential activity changes that might have occurred as it traveled from Jupiter's orbit inward toward the Sun. Future objects detected by Rubin Observatory might be monitored from distances beyond Saturn's orbit, providing years of observation time instead of months. This extended observation period will enable entirely new types of scientific investigations. Dr. Colin Snodgrass's research on long-period comets demonstrates how multi-year monitoring campaigns can reveal subtle changes in activity patterns, rotation rates, and structural integrity that provide insights into internal composition and thermal evolution. Applied to interstellar objects, such long-term studies might reveal whether their anomalous behaviors develop gradually or represent fundamental differences from solar system objects. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents the next generation of spacecraft designed specifically for studying pristine cometary objects. While originally planned to study a long-period comet from the Oort cloud, mission planners are developing protocols for redirecting the spacecraft to intercept interstellar visitors if suitable targets are discovered during the mission's operational period. Dr. Geraint Jones, the Comet Interceptor project scientist, describes how close proximity observations could resolve many of the mysteries surrounding objects like 3.1 ATLAS, insider measurements of gas composition, dust particle analysis, nuclear morphology mapping, and magnetic field detection would provide data quality impossible to achieve with Earth-based telescopy. A single flyby mission could answer more questions about interstellar object properties than years of ground-based observations. The technical challenges of intercepting interstellar objects require revolutionary advances in spacecraft design and mission planning. Unlike solar system objects that follow predictable orbits, interstellar visitors arrive from random directions with hyperbolic trajectories that provide limited time for mission planning and spacecraft deployment. Dr. Andy Rivkin's research on rapid response mission concepts reveals the need for pre-positioned spacecraft or revolutionary propulsion systems capable of achieving intercept trajectories within months of target detection. NASA's proposed rapid response missions for interstellar object intercepts represent an even more ambitious approach to studying these cosmic visitors. Dr. Julie Castillo-Rojas' mission concepts involve spacecraft parked at gravitational balance points in the outer solar system, ready for immediate deployment when new interstellar objects are detected. These missions could potentially reach targets within months rather than years, enabling detailed study of objects that might otherwise pass unnoticed. The concept of Sentinel spacecraft stationed throughout the outer solar system represents a paradigm shift in planetary defense and scientific exploration. These robotic guardians would serve dual purposes, detecting potentially hazardous asteroids and comets while simultaneously preparing to intercept scientifically interesting interstellar visitors. Dr. Lindley Johnson's Planetary Defense Coordination Office has begun incorporating interstellar object intercept capabilities into future mission architectures. Advanced propulsion technologies currently under development could revolutionize our ability to study interstellar objects through active pursuit rather than passive observation. Dr. Bruce Wheatman's research on solar sail propulsion suggests that large, lightweight spacecraft could potentially match velocities with interstellar objects, enabling extended observation periods that dwarf the brief flyby encounters possible with conventional propulsion. The theoretical future for understanding 3I Atlas lies in advances in computational modeling and laboratory astrophysics that might reproduce its anomalous behaviors under controlled conditions. Dr. Alicia Weinberger's team is developing sophisticated ice sublimation models that incorporate quantum mechanical effects, exotic ice phases, and non-equilibrium chemistry that might operate in interstellar environments, but not in terrestrial laboratories. These computational models are approaching the sophistication needed to predict the behavior of exotic cometary materials under conditions that have never been tested in laboratories. Dr. Murthy Judipati's work on amorphous ice phases reveals that water ice can exist in multiple crystalline structures with dramatically different sublimation properties. Under the extreme conditions of interstellar space, ice might transform into phases that sublimate with efficiency far exceeding normal hexagonal ice. Laboratory experiments simulating million-year interstellar journeys represent another frontier in understanding objects like 31ATL-S. Dr. Helen Fraser's ultra-high vacuum facility can expose ice samples to cosmic ray bombardment and extreme temperature cycling for extended periods, potentially revealing structural and chemical changes that might explain the anomalous properties observed in interstellar visitors. The challenge of laboratory simulation involves recreating not just the extreme cold and radiation of interstellar space, but the timescales involved in interstellar journeys. Dr. Reggie Hudson's research on radiation chemistry in ices has revealed that cosmic ray bombardment over million-year periods could create chemical, species, and structural modifications that don't occur under shorter laboratory exposures. Advanced experimental techniques using accelerated aging protocols might compress million-year processes into laboratory-accessible timeframes. Advanced computational fluid dynamics simulations are approaching the capability to model gas dynamics around irregularly shaped, rotating nuclei with complex internal structure. Dr. Jean-Baptiste Vincent's team is developing codes that can simultaneously track thermal evolution, internal chemical reactions, structural changes, and gas dynamics to create comprehensive models of how exotic comets might behave under solar heating. These next-generation models incorporate quantum mechanical effects in ice sublimation, non-equilibrium chemistry in gas plumes, and electromagnetic effects in ionized cometary atmospheres. The computational requirements are enormous, demanding supercomputer resources that can track millions of individual particles while solving complex physics equations across multiple scales from quantum to macroscopic. The future of spectroscopic analysis lies in next-generation extremely large telescopes that will provide unprecedented sensitivity for studying faint, distant objects. The extremely large telescope, with its 39-meter primary mirror, will collect nearly 15 times more light than current 8-meter telescopes, enabling detailed spectroscopy of interstellar objects that remain undetectable with current instrumentation. Dr. Ewan van Dishoek's research on molecular spectroscopy in extreme environments suggests that advanced spectrographs on extremely large telescopes might detect previously unknown molecular species in interstellar objects. These observations could reveal chemical processes that don't operate under solar system conditions, but might be common in other stellar environments. The spectroscopic revolution will extend beyond individual molecular detections to comprehensive chemical fingerprinting that could identify the parent stellar systems of interstellar visitors. Different stars have distinct patterns of element abundances based on their formation environments and evolutionary histories. Dr. Maria Lugaro's work on stellar nucleosynthesis suggests that detailed isotopic analysis of interstellar objects might reveal whether they formed around low-mass stars, massive stars, or in exotic environments like binary star systems. Space-based infrared astronomy will undergo revolutionary advances with the James Webb Space Telescope's capabilities for studying small solar system bodies. Dr. Stephanie Millam's team has demonstrated Webb's ability to detect water vapor, carbon dioxide, and complex organic molecules in cometary Comet with sensitivity far exceeding previous infrared observatories. Future interstellar visitors might be studied with molecular specificity that was impossible for 3I Atlas. The infrared wavelength regime provides access to molecular vibrations and rotational transitions that reveal detailed information about temperature, density, and chemical composition in cometary Comet. Webb's unprecedented sensitivity in this wavelength range could detect molecular species at abundance levels, orders of magnitude, lower than current ground-based capabilities, potentially revealing trace constituents that provide crucial clues about formation environments. Advanced coronagraphic techniques being developed for exoplanet detection could be adapted for studying the internal structure of cometary nuclei. Dr. Laurent Pueyo's research on high-contrast imaging suggests that space-based coronagraphs might be capable of resolving surface features and active regions on interstellar object nuclei, providing morphological information that ground-based telescopes cannot achieve. The emerging field of multi-messenger astronomy offers new approaches to studying anomalous objects through coordinated observations across electromagnetic, gravitational, and particle channels. While interstellar objects like 3I Atlas are unlikely to produce gravitational waves or high-energy particles, the systematic approach of multi-messenger observations might reveal subtle signatures that single-wavelength studies miss. Dr. Laura Catenati's work on gravitational wave astronomy has revealed how sensitive modern detectors have become to slight disturbances in spacetime. While interstellar objects don't produce detectable gravitational waves through their normal motion, theoretical work by Dr. Abraham Loeb suggests that rapidly rotating or fragmenting interstellar objects might produce gravitational signatures detectable by future generation gravitational wave observatories. Neutrino astronomy represents another frontier that might provide insights into interstellar objects. Dr. Francis Housen's IceCube Neutrino Observatory has demonstrated the ability to detect high-energy neutrinos from astrophysical sources. If interstellar objects contain radioactive isotopes or experience nuclear reactions during solar heating, they might produce neutrino signatures that could be detected by next-generation neutrino telescopes. Artificial intelligence and machine learning applications to astronomical data analysis are already revealing patterns in complex datasets that human analysts might miss. Dr. Megan Schwalm's work applying machine learning to asteroid and comet characterization suggests that AI analysis of comprehensive datasets from future interstellar objects might identify correlations and behaviors that resolve current mysteries about anomalous acceleration and chemical composition. Machine learning algorithms trained on large datasets of solar system comet behavior could identify subtle patterns in interstellar object observations that distinguish natural from potentially artificial characteristics. Dr. Darren Ragodseen's research on machine learning applications in planetary science demonstrates how AI can detect complex orbital relationships and compositional patterns that would require years of human analysis to identify. The development of autonomous spacecraft with AI-driven, scientific decision-making capabilities could revolutionize interstellar object studies. Dr. Steve Chen's work on autonomous mission planning suggests that future spacecraft could adapt their observation strategies in real time, based on detected anomalies or unexpected behaviors, maximizing scientific return from brief encounter opportunities. The theoretical future includes potential breakthroughs in fundamental physics that might explain not only 3.1 ATLAS properties, but also broader cosmic mysteries involving dark matter, dark energy, and modified gravity. If interstellar objects serve as sensitive probes of gravitational physics, their anomalous behaviors might provide crucial tests of theories that attempt to unify quantum mechanics and general relativity. Dr. Catherine Freese's research on dark matter interactions suggests that interstellar objects might serve as detectors for exotic particles or forces that don't interact significantly with ordinary solar system matter. If 3I Atlas encountered dark matter concentrations during its interstellar journey, this interaction might explain some of its anomalous properties while providing insights into dark sector physics. The possibility that interstellar objects could serve as dark matter detectors has profound implications for fundamental physics. Unlike terrestrial dark matter detection experiments, which search for rare particle interactions in underground laboratories, interstellar objects have traveled through galactic environments with varying dark matter densities for millions of years. Any accumulated effects from dark matter interactions might be detectable through careful analysis of their trajectories and physical properties. Quantum gravity effects, typically important only at the Planck scale, might become observable in objects that have experienced extreme conditions during interstellar travel. Dr. Carlo Rovelli's work on loop quantum gravity suggests that spacetime itself might have granular structure at microscopic scales. Interstellar objects that have interacted with cosmic ray particles at extreme energies over million-year periods might preserve signatures of quantum gravitational effects. The astrobiological implications of future interstellar object studies might revolutionize our understanding of life's distribution throughout the galaxy. If objects like 3I Atlas serve as vehicles for transporting organic molecules or even microorganisms between stellar systems, detailed biochemical analysis of future visitors might provide direct evidence for panspermia or extraterrestrial biochemistry. Dr. Sarah Seeger's research on biosignature detection suggests that advanced spectroscopic analysis of interstellar objects might reveal organic molecules with isotopic ratios or structural complexity that indicates biological origin. Such discoveries would transform interstellar visitors from astronomical curiosities into astrobiology laboratories carrying samples from alien worlds. The search for amino acids, DNA bases, and other biological molecules in interstellar objects requires analytical techniques that push the boundaries of current spectroscopic capabilities. Dr. Jason Dworkin's research on organic compounds in meteorites demonstrates the sophisticated chemical analysis needed to distinguish biological from abiological organic synthesis. Future space missions to interstellar objects might carry mass spectrometers and chromatographic equipment capable of performing such analysis. The possibility of detecting living microorganisms in interstellar objects represents the ultimate astrobiological discovery. Dr. Lynn Rothschild's research on extremophile organisms has revealed life forms capable of surviving conditions approaching those of interstellar space. If microorganisms can survive million-year journeys in the ice matrices of interstellar objects, they might provide direct samples of alien life arriving at Earth's doorstep. Advanced sample return missions to interstellar objects could bring pristine extraterrestrial material to Earth for analysis with laboratory techniques impossible to deploy in space. Dr. Donald Brownlee's experience with the Stardust mission demonstrates how sample return provides analytical capabilities orders of magnitude beyond what spacecraft can achieve. Interstellar object samples might reveal biochemical signatures, isotopic anomalies, or structural features that definitively establish their extraterrestrial and potentially biological origin. The long-term future of interstellar object research might involve active missions to pursue objects like 3I Atlas into interstellar space, maintaining observations long after they've left our solar system. Dr. Robert McNutt's concepts for interstellar precursor missions suggest that suitably designed spacecraft might accompany interstellar objects on their journeys between star systems. Such missions could provide unprecedented insights into how objects behave in true interstellar space, where the solar wind and solar radiation that complicate observations within our solar system are absent. Long-term monitoring might reveal whether 3I-ATLAs, as anomalous properties, represent temporary responses to solar system conditions or fundamental characteristics that persist throughout interstellar travel. Interstellar escort missions would require revolutionary propulsion technologies capable of matching the extreme velocities of interstellar objects. Dr. Philip Lubin's research on photonic propulsion suggests that laser-powered light sails might achieve sufficient velocities to accompany interstellar visitors, providing long-term monitoring capabilities that conventional chemical propulsion cannot match. The technical challenges of interstellar escort missions extend beyond propulsion to communication, power generation, and autonomous operation across interstellar distances. Spacecraft accompanying interstellar objects would need to operate independently for decades or centuries, making scientific decisions and transmitting data across light years without human intervention. Dr. Lou Friedman's work on deep space exploration architecture suggests that such missions might serve as testbeds for true interstellar exploration technologies. The ultimate revelation about 3I Atlas and objects, like it might come through direct contact either through sample return missions that capture material from interstellar visitors, or through the discovery that some interstellar objects are indeed artificial constructs carrying messages or technologies from other civilizations. Dr. Abraham Loeb's proposals for active monitoring of interstellar objects for potential technological signatures represent a new frontier in SETI research. If future objects exhibit clear evidence of artificial origin, they might provide humanity's first definitive proof that we're not alone in the universe. The search for technological signatures requires developing detection methods for artificial materials, geometric structures, or electromagnetic emissions that would distinguish engineered objects from natural ones. The discovery of definitively artificial interstellar objects would trigger protocols for international cooperation and scientific investigation unprecedented in human history. Dr. John Rummel's work on planetary protection suggests that contact with extraterrestrial technology would require careful quarantine and analysis, procedures to prevent contamination while maximizing scientific understanding. Advanced materials science might eventually enable the construction of interstellar probes with capabilities that dwarf current spacecraft technologies. Dr. Zach Manchester's research on femtosatellites and chip-scale spacecraft suggests that future interstellar exploration might involve swarms of tiny intelligent probes capable of comprehensive scientific surveys while remaining virtually undetectable to current astronomical instruments. The possibility of human-built interstellar objects being detected by other civilizations raises questions about how we might design our own interstellar emissaries to maximize scientific and cultural information transfer. Dr. Frank Drake's experience with interstellar message design suggests that effective communication across interstellar distances requires fundamental assumptions about mathematics, physics, and logic that might be universal among technological civilizations. As we look toward a future where interstellar visitors might become routine subjects of study rather than rare anomalies, 3.1 a TLAS stands as a harbinger of discoveries that might fundamentally transform our understanding of cosmic evolution, planetary formation, and the possibility of life throughout the galaxy. The mysteries it leaves behind will drive scientific exploration until the day when new observations, new technologies, and new theoretical insights finally unlock the secrets it carried from the stars. The convergence of advanced detection capabilities, revolutionary space technologies, and sophisticated theoretical frameworks suggests that the next decade will witness unprecedented advances in interstellar object research. Each new visitor might provide crucial pieces of the puzzle that 3I Atlas began, gradually revealing the true nature of these cosmic wanderers and their role in the galactic ecosystem of matter and information exchange. The legacy of 3I Atlas extends beyond its individual mysteries to the Recognition that our solar system exists within a dynamic galactic environment where matter, energy, and potentially life itself flow between stellar systems in patterns we're only beginning to understand. The future revelations promised by this enigmatic visitor might ultimately show us that the universe is far more interconnected, far more active, and far more wondrous than our earthbound perspective has ever allowed us to imagine. Throughout this investigation into one of astronomy's most perplexing contemporary mysteries, we've discovered that 3I Atlas represents far more than a single anomalous comet. It's a cosmic Rosetta Stone that challenges our fundamental understanding of how objects behave in space, how comets form and evolve, and what kinds of exotic phenomena might exist in the vast interstellar wilderness between stars. We've seen how this enigmatic visitor violated nearly every principle we thought we understood about comet physics, accelerating without sufficient outgassing, fragmenting in controlled patterns unlike any natural breakup, and exhibiting chemical compositions that suggest formation in stellar environments utterly unlike our solar system. Each observation revealed new puzzles rather than resolving existing mysteries, creating a cascade of questions that push the boundaries of current astronomical knowledge. Perhaps the most profound insight is that 3I Atlas forces us to confront the limitations of our solar, system-centric understanding of cosmic objects. We've built our theories of comet physics based on objects that formed within our own solar nebula, orbited our own sun, and evolved under the specific conditions of our local cosmic environment. But the universe contains countless stellar systems with different masses, compositions, and evolutionary histories that might naturally produce objects with properties we consider impossible. The implications extend far beyond academic astronomy to fundamental questions about the cosmic environment we inhabit. If interstellar space is filled with objects like 3I Atlas visitors carrying information about exotic stellar environments, light years from Earth, then our solar system exists within a cosmic library of astronomical specimens that could teach us about astrophysical processes we might never otherwise study directly. As you contemplate the night sky after learning about this interstellar mystery, remember that objects like 3I Atlas might be passing through our solar system regularly, carrying secrets from distant stars while remaining invisible to our current detection capabilities. The universe around us might be far more dynamic and interconnected than we've ever imagined, with material constantly flowing between stellar systems in a galactic ecosystem of cosmic exchange. When you consider the chemistry of 3I Atlas, its exotic isotope ratios and unusual molecular abundances, you're encountering evidence of stellar nucleosynthesis processes that operated around other stars potentially billions of years ago. The deuterium-rich water detected in its spectrum might have formed in molecular clouds colder than anything in our solar system, preserving chemical signatures of conditions that existed when our galaxy was young. The mysterious physics of 3I Atlas's acceleration and fragmentation reveals how little we understand about the behavior of matter under cosmic conditions. The same quantum mechanical and thermodynamic principles that govern chemistry and physics on Earth operate throughout the universe, but they might produce phenomena under interstellar conditions that we've never observed in terrestrial laboratories or solar system objects. You are connected to these cosmic processes through the very atoms in your body, which were forged in stellar nucleosynthesis and distributed through space by processes similar to those that might have created and ejected 3I Atlas from its parent stellar system. The carbon in your DNA, the oxygen in your blood, and the calcium in your bones might have spent millions of years traveling through interstellar space before condensing into the solar nebula that formed our planetary system. The search for explanations of 3I Atlas as anomalous properties has pushed astronomical instrumentation to its limits and revealed the urgent need for new technologies designed specifically for studying interstellar visitors. The next generation of telescopes and space missions will provide unprecedented capabilities for detecting and characterizing these cosmic wanderers, potentially transforming them from rare curiosities into routine subjects of study. But perhaps the most important lesson from 3IATLS is that the universe consistently surprises us with phenomena that transcend our current theoretical understanding. Every major advance in astronomy has been driven by observations that didn't fit existing models, forcing scientists to expand their conception of what's possible under natural conditions. 3.1. A TLAS joins a distinguished lineage of astronomical anomalies that have challenged and ultimately advanced human knowledge. The mystery of 3IATLAs also highlights the collaborative nature of modern astronomical research. Resolving its puzzles required observations from dozens of telescopes around the world and in space. Coordinated campaigns involving hundreds of astronomers and theoretical work spanning multiple disciplines from planetary science to fundamental physics. No single observatory or research group could have characterized this object adequately. If this exploration of 3I Atlas has expanded your appreciation for the mysteries that still pervade our understanding of the cosmos, share it with others by subscribing and giving this video a thumbs up. Check out my video on the mystery of Amamo, where we dive into the first confirmed interstellar visitor and its equally puzzling properties. I think you'll find the comparison fascinating. The next time you see a bright comet in the night sky, remember that you might be witnessing phenomena that operate according to physics we don't fully understand, powered by chemistry that formed under conditions unlike anything in our solar system, and carrying information about cosmic environments that might be fundamentally different from our local galactic neighborhood. What have we learned about 3IATLAs? That the universe is far stranger and more wonderful than our solar system-based theories predicted. That interstellar space might be filled with objects whose properties challenge our most basic assumptions about how matter behaves under cosmic conditions. And that the cosmos continues to present us with mysteries that reveal how much we still have to learn about the universe we inhabit. 3.1 ATLAS is not behaving like a normal comet because it isn't a normal comet. It's something exotic and unprecedented that has forced us to confront the limitations of our current understanding and open new frontiers in astronomical research. Whether it represents an extreme example of natural comet evolution or something even more extraordinary, it has forever changed how we think about the objects that visit our solar system from the depths of interstellar space. The greatest discoveries in science often begin with the simple observation that something isn't behaving as expected. 3IGUS has provided exactly such an observation, and its legacy will continue to drive astronomical research until we finally understand what makes this cosmic visitor so remarkably, mysteriously different from everything else we've seen.